We can still switch to talk, so you can go.
Sipash,
Yes.
can you try sharing your screen so that?
Can you see my screen?
Yeah, I can.
Yeah.
Yes.
Right. I can start?
Yeah, sure.
And can you all hear me well? If not, just let me know.
You are audible.
Okay, great. So good afternoon. Thank you for having me here. So this is the outline of my talk. I will start by briefly introducing the mathematical framework of the lattice QCD, and then I will pick two problems that I led the investigation for. And these two problems focus on the non-perturbative aspects of QCD, deconfinement, and chiral phase transition. So the first subtopic would be studying deconfinement on the lattice using open-charmed states. And the second would be probing three-flavor chiral phase transition using lattice QCD approach. And if the time permits, I will also show you some preliminary investigations of the ZB tetraquark channel. And because in the isospin 0 case, these tetraquark operators can give you a hallmark signature of confinement. And each problem will have its own motivation, conclusions, and future plan slides. So let's start with the QCD Lagrangian. I'm sure you have seen it multiple times. So F is the field strength tensor, which also incorporates the gluonic self-interaction. Then there is the covariant derivative. Each spinor carries Dirac, color, and flavor indices. Flavor can be up, down, strain, charm, top, bottom. But keep in mind that on lattice, we can vary the number of flavors as well as the quark masses. Let's go to the QCD running coupling. We know that the beta function of QCD tells us how the strong coupling changes with the, or how it is dependent upon the scale. And this is the familiar one loop solution, which and here beta naught is the one loop perturbative expansion parameter, lambda is the overall scale parameter. And you can see in this plot, so alpha s is alpha strong, which is g squared by 4 pi. So you see in this plot, as we go to high energies or q tending to infinity, the coupling goes to 0, which means that the theory is asymptotically free. And if we look at the beta function in its perturbative form, we can see it can be expanded around this point. And here beta naught is again the perturbative one loop expansion coefficient, which I showed you on the previous slide. So as long as 11 is greater than 2/3 of the number of flavors, which is the case for 6 flavors, we will have a beta function which is negative. So this is the asymptotically free fixed point or the UV fixed point, and the perturbation theory tells us that that is how the beta function looks like. But what about when coupling is large? This is the non-perturbative region, and to get the information about this physics, we need to do lattice. So when we do lattice, we discretize the Euclidean space-time. We place fermions on the side and gauge fields as the parallel transports on the links. And the familiar one loop expression, it takes the form where q square gets replaced by 1 by a, and a is the lattice spacing. And think of lattice as blocking transformation in terms of Wilsonian RG. So because we are doing the blocking transformation, one would generate irrelevant couplings as well. So let's just say we only had one relevant direction in the continuum theory, but as we do the blocking transformation, we can get more couplings like G2, G3, and I can only draw 3 couplings, so I only drew 2 here, 2 irrelevant couplings here. So which means now this point will lie on a critical surface and it will have an attractor, which could be the Gaussian fixed point, because here the coupling would be 0. And the continuum physics would be determined by the direction, by the renormalization direction of the relevant coupling, or you can call, and you see when you, and now you can, let's say your bare action parameter, you start somewhere here. as you flow in the RG space, ultimately all these irrelevant couplings should die and you will get the continuum physics. Similarly, you start from here, you will approach the continuum physics. So this is, very briefly, I would say that is how the lattice works. And yeah, I should just emphasize that at this critical surface, correlation length is infinity, which also means that we take the lattice spacing to 0. So think of lattice as a regulator um, uh, with UV cutoff A, or because we use periodic boundary condition and discretization, which also makes it periodic in momentum. So the momentum cutoff is pi by A. And so we get the regulator, as well as we can do Monte Carlo sampling of the partition function, and it becomes a calculable problem. So that is what lattice is in a nutshell. Now let's go to charm physics. Why do we want to do open charm?
Ashifa, so
Yeah.
are you telling that lattice is just a regulator, or it has some special properties? Can any cutoff regulator give you this kind of a physics, or has some special properties which are very important for our calculation?
I mean, I would say lattice is a regulator, and then it gives you the non-perturbative renormalization, which you cannot get from the perturbative beta function.
Yeah, I would rather say that it is also preserve the anomaly. So that is very important. Any cutoff regulator doesn't preserve the anomaly. So that lattice regulator actually preserves anomaly. And that is very important aspect of lattice-based theory. That it is a gauge invariant anomaly free regulator.
Yes, it is a yeah, that's true. It is a gauge invariant anomaly free. Like yes, it is. It is. Yeah.
Because if you just put a cutoff, the gauge invariance is not guaranteed. So that's not quite.
Yeah. Okay, thank you.
Sorry, can I ask one question?
Yeah.
Sorry, is it easy to explain why you have more couplings than what you started out in the company?
You can just I mean, from Wilsonian RG, you know, when you do blocking transformation, you want to match your action to the blocked action, and that results in more and more couplings. But then these couplings are irrelevant because of their, because there's this that D should be greater than the power of the coupling and divided by P half minus 1. Does that make sense?
No, you should continue. It's fine. Yeah.
Sorry?
You should continue. I'm not sure I got the answer, but you should continue. It's fine.
Okay, but I can repeat my answer if you want to.
No, probably it'll take you off topic. You should continue. It's fine.
Okay, so the next topic is we want to do open charm physics on lattice. Why do we want to do it? Because we know that the strong interaction matter, it undergoes a chiral crossover at the pseudocritical temperature given by this value. And in the heavy ion collision experiments, the relevant degrees of freedom, they change from partonic to hadronic in going from high temperature phase to low temperatures. But what happens to charm hadrons? Do they start melting at this chiral crossover temperature? And how do we check that? We compare the lattice results with a very successful HRG model, which has been quite successful in describing the particle abundance ratios found in collision experiments. Okay, let's just say if charm hadrons start melting at TPC, what are the relevant degrees of freedom after the onset of the hadron melting? And can we get a signal for the appearance of quarks above this chiral crossover temperature? And even if charm hadrons start melting at TPC, doesn't mean that they just melt right away. It is a crossover transition. So when do they actually stop contributing to the total charm pressure? So these were the kind of questions I wanted to ask.
What do you mean by melting here?
What do I mean by melting here? Okay, so right now, my definition of melting would be based on departure from HRG. Okay, that's a very crude way of calling it melting. So throughout this talk, you will see my melting is based on departure from HRG, but in my future plans, I will tell you I want to make this definition more concrete.
No, but as you know, as you already mentioned, the HRG always assume point like baryons or mesons.
Yes, yes, that's true.
And this charm-like excitations may remain, but with a width. So those I would not call as hadrons. Even though it is a crossover, it doesn't mean it will stay in the medium. These are not
but
zero temperature hadrons, but these are finite
Yeah.
temperature ones.
yes,
And
so these
yeah.
so these could be thermally modified, or their widths are increasing as the temperature increases,
yeah,
because
that we should not call as hadrons. So
well,
excitations in the medium, broad excitations.
right, but it also depends if in a given channel the separation between let's say two peaks is larger than the width, then we can call them independent hadrons.
But
It's a
we
matter
can-
of how you define it. But let's say if the separation between two peaks is less than their width, then we cannot call them. Then they're overlapping and we are overcounting the number of degrees of freedom.
and
But if they're well,
you should be very
Yeah.
careful, because if we studied it, all the excited states are very broad. So they may overlap very strongly, like around 3 GeV or so. So those things are or above those. So one has to be careful about those things.
yes, so that is exactly my point. I don't want to overcount the number of degrees of freedom. And the states which you are mentioning above 3 GeV, they anyway don't count that much to HRG, right? Because their Boltzmann weight is really suppressed. But since you asked for the definition of hadron, in my mind, that is the definition, that as long as they are separated enough and their width is small in comparison to the separation, I would still call them hadrons, and like independent hadrons, even if they are slightly broadened. But if they are really broadened, then I would say we are overcounting the number of degrees of freedom, as you said. Yeah.
And
But-
also, one more thing is that even if it is 3 GeV,
Yeah.
the multiplicities are very high. So in the hadron resonance gas model, the multiplicity term turns the e to the power. So
I
those
think
are high. So for these higher excited states. So
yeah,
so the exponential part is suppressed, but the multiplicity term is very strong. So
yeah, actually,
signatures of those in the HRT.
I understand your question. Actually, I did this calculation explicitly, and I checked that if I remove states above 3 GeV, I still get an agreement with the full HRG within 1%. So I actually did this calculation. I checked it explicitly, so it should be fine.
And do you know why for charm the HRG works so well?
Why HRG works so well for charm?
Yes.
I would say it also, first thing is the Boltzmann approximation. So we can throw out higher orders, but it also works well for light hadrons.
Oh,
In
for
fact-
light hadrons, they come with ether that the repulsive interactions
Sure,
become very
okay.
common after 145 millimeters. If you look at baryon strangeness correlators, it is way away from the hadron resonance gas model. If you look at pressure, then it is fine because pressure is dominated by mesons. But all these baryon strangeness correlators, they are way off. Even at
Yeah. I know there could also be like decays of delta, all those kinds of things. But I think for charm, the answer is it's because of the Boltzmann.
of the baryons, which becomes very important when the baryons start propping up. But why in this case it is so much subject?
Because of the heavier charm mass.
Maybe you can think of it later, maybe you can proceed.
Okay. All right. So we can basically, to tap onto these degrees of freedom, we can look at derivatives of pressure with respect to different chemical potentials. And pressure is just related to the partition function, and you can Taylor expand it. And these coefficients are also known as the generalized susceptibilities, and they are just derivatives of pressure with respect to the charm chemical potential, strangeness, electric charge, and baryon number. And on lattice, the volume would be lattice spacing times the number of points in the spatial direction, or the spatial lattice extent. Temperature would be the inverse of A times n tau, and tau means the temporal lattice extent. And you can see immediately that at a fixed temperature, if you want to go to the continuum limit, you have to take larger and larger n tau. So I cannot give you the details right now, but these derivatives of pressure on the lattice, they can be calculated using unbiased stochastic estimation, and they comprise of various traces of inversions and derivatives of the fermionic matrices. Wait, I was talking about renormalization and other things, and we need to first set the scale on lattice for lattice spacing and the quark masses. So just some details. I reused the high statistics configurations generated by hot QCD collaboration to study equation of state and other things. These configurations were generated using highly improved staggered Cork action, and there were like 3 temporal lattice extents. The aspect ratio was fixed to 4. The charm was treated in the quenched approximation. So we need to set the scale. The strange mass was tuned by fixing this fictitious pseudoscalar mass to its value, chiral perturbation theory value. Lattice spacing was fixed using the kaon decay constant, and we also had to fix charm quark mass. So I'm just giving you one example here. For example, if you want to fix the charm quark mass on lattice, for each value of beta is the inverse coupling. Let's just pick 6.285. At a given coupling value, you use trial values of the bare charm quark mass, and then you see its intersection with the physical charmonium mass.
What do you mean by
Sorry?
What do you mean by a charmonium view? Which specific thing are you considering?
This is spin averaged charmonium. So eta CC, yeah, and
And which one?
and JPSI. It's spin averaged. Both 1s, but spins zero scalar and the vector.
Yeah.
Okay. Yes. So then you pick these intersections and then you fit them by a renormalization group inspired ansatz, and you get your parameterization of AMC as a function of beta, or the gauge coupling. You will see that to understand the cutoff effects in charm, we had to do tuning using different lines of constant physics, and let's call this charmonium LCP, LCPA. So now we did our first calculation. Here you see we did our calculation for n equal to 8, which approximately corresponds to lattice spacing of 0.16 Fermi at t equal, and this is TPC with its errors. These are the lattice data points, and this is the HRG curve. I will explain to you later what is QM-HRG. Let's just think it's HRG curve, and you see at TPC, there's a difference of 2.7 between these two curves. The data lies below the HRG curve. So why was this happening? So if you think about it, in the HRG, each charm hadron contributes with this Boltzmann weight. So which means and charm quark is heavy, heavier than the light quarks, for example. And if there's a small change in the charm quark mass, it would lead to a large change in the Boltzmann weight. So this means we should focus on the most thermodynamically dominant charm hadron for the kind of physics we want to do. So, and by the way, this formula is also valid for the case of charm quarks, because they are also quite heavy. And but we did remove these order AMC4 cutoff effects from the action. And the action which we are using, it's known to give sub% errors when AMC is of the order 0.5 or lattice spacing is 0.08. And like I told you, this lattice spacing was for 0.16, so we still had hope. If we go to final lattice spacings, we could get results closer to the physical expectation, but we still wanted to investigate the cutoff effects. So at n equal to 8, I did the calculation for the d meson masses, and I found out that...
Hello?
Yes?
Can you go back to the previous slide?
This one, or?
Yeah, in this scale, where is the critical temperature for the same system?
This yellow band is the critical, the crossover temperature.
And why do you have this HRG curve on the right?
Why do I have the HRG curve on the right? On the right, here.
That's supposed to be more QCP-like than hadron gas, right?
Yeah, but see, I can draw the QM-HRG curve, right? It only contains hadrons. Nothing stops me from...
it's made up of hadrons and extrapolate.
See, I can do the calculation. Nothing stops me from plotting this HRG curve, even for larger temperatures. What matters is how the data behaves with respect to this HRG curve, and I will show you later that if you look at the right quantities, they will have agreement with HRG and then they will deviate. Maybe I should just go and show you here, for example. This is the HRG expectation, and then the data deviates from the HRG expectation. And you need to draw the HRG curve to show that it's deviating from HRG. Does that make sense?
But it may not have anything to do with the quark-gluon plasma, right?
No, this HRG curve only has hadrons. It has nothing to do with the quark-gluon plasma. The lattice data will tell you.
My concern was we are taking into a temperature where it may not be physically relevant.
Yeah, exactly. And that is the whole point. I want to show that it's not physically irrelevant by posing the comparison with the lattice data. Exactly.
Yeah, we can.
Okay. So this was motivated by the thermodynamics, and for the LCP, which was tuned using the charmonium mass, we found that only for the finer lattices, the d meson mass was close to its physical values, but for coarser lattices, the d meson mass was away from the physical value. And so then what did we do? So this is the proxy for the charm pressure as a function of temperature. Let's just pick one temperature, okay? Let's just pick 156 MeV, which is here. We had 3 data points for this case. So we had calculated this quantity for 3 different LCPs. One was fixed using the charmonium mass. Second was fixed by using the ratio of strange quark to charm quark mass. And third was already fixed using charmonium, but with a different renormalization group in Spiron-Zars. It was from the paper of Shayantan, by the way. So what did we do? We said, okay, this log of chi4c should be linear in the charm quark mass. And because the Boltzmann weight of the d meson mass, the thermodynamically dominant hadron would be this. And you can see this in this inset. It is actually the case. And then we also tuned the charm quark mass using d meson, and then we picked those points from here. And then we constructed the d meson LCP, which are these blue data points, and then they are interpolated using this 2-2 pade. So it was really a big bottleneck to crack, taking the continuum limit, because we wanted to compare our results with experiments. And then we repeated the same procedure for n dot 12 and 16, and then we obtained the continuum estimate for this pressure. And you would say, okay, you only took continuum limit for this quantity. What about other quantities? Well, we had strong indications, and we show that in our paper, that the ratios of these quantities actually they are not cutoff dependent, and they do not depend upon the charm quark mass either. So let's just say I'm interested in something like chi BC13. I can just calculate chi BC13 normalized by this quantity on a coarser lattice, and then take the continuum limit and remove that normalization, and I will get the continuum estimate. So we had to be clever, and yeah, that's how we got the continuum limit of these things. Okay. And just a quick recall, this is HRG. The pressure of the charm pressure can be split into meson, and the baryon contributions and the Boltzmann approximation works. And to these susceptibilities, each hadron contributes with a weight that depends upon their quantum numbers. And at high temperature, the Boltzmann approximation also works for a free gas of massive charm quarks and antiquarks. So now, let's look at quantities which are independent of the hadron spectrum, and they take a definite value in the HRG, a particular value in the HRG phase and a different value in the high temperature phase. So we looked at this quantity, which is chi BC13 divided by chi BC22. Because charm hadrons are quite massive, we expect both of them to be equal and to project onto the baryon charm pressure, and they should stay 1 as long as HRG is valid, and they should deviate from 1 when HRG stops being valid. And you see, this is the TPC. Exactly at TPC, these data points deviate from unity. They tell us that some new degrees of freedom are appearing at TPC, and at around 330 MeV, it's like 10% below its ideal charm quark gas value. So which is it's approaching that. So we know the carriers of the charm degrees of freedom in the low temperature phase, and we know the carriers of the charm degrees of freedom in the high temperature phase. Shantan, in one of his papers with his collaborators, he posed a quasi-particle model. They were like, okay, why not let's just extend the HRG model to also allow the presence of charm quarks. And in the next slide, I will show you how these pressures looked like. Unfortunately, in the case of Shantan, they did not have continuum limit, as well as they had really high statistics, and the crossover region was also very wide. So it wasn't very conclusive, but now you see in this plot, let's just start with the mesonic pressure. So this is how the mesonic pressure looks like, and this is the expression for that. Data points, you see these red data points, they're from lattice. And you see HRG curves of different types. PDG HRG means I only include states tabulated in the tables of PDG. So the experimentally known states. QMHRG means in addition to the PDG states, I'm also including states which are predicted by the quark model but are not yet experimentally discovered. And 1S, 1PHRG means I'm only including the low-lying states and their parity partners. So for the sake of this slide, just ignore 1S, 1PHRG. So you see the data agrees very well with QMHRG, and then it departs from the QMHRG, which is what we want. It also shows that the new degrees of freedom are originating at TPC, and that is why QMHRG is not valid anymore. Same for the case of the baryon pressure. Now you see here enhancement factors. So these enhancement factors mean lattice data at TPC divided by the PDG HRG expectation. So here you see it means only like 13% contribution to the mesonic pressure, charm mesonic pressure, comes from experimentally unobserved states. But for the case of baryons, around 50% contribution comes from the baryons or the charm baryons that are yet experimentally undiscovered, which is a big thing. That lattice could predict this, and QMHRG totally agrees with the lattice data. In addition to that, we could also calculate the quark pressure, and we have a very nice non-zero signal above TPC. The quark pressure is rising. It's by construction 0 below. So in a way, this is a novel parameter for deconfinement. And also, people from ALICE, they took these enhancement factors and they used it to fit their experimental yields of open charm baryons, and it really worked for their data.
Why do you call it deconfinement?
Sorry?
Why do you call it as a deconfinement parameter?
Because the appearance of particles with the quantum number of charm quark, it clearly shows that we have degrees of freedom which carry the quantum numbers of charm quark. So this is deconfinement, isn't it?
But we saw that these are open charm hadrons. So
yeah,
their area and everything are very close to the light hadrons. They should be sensitive to the chiral symmetry of this light quarks.
They should be sensitive to the chiral symmetry of what?
Of the light quarks.
Of the light quarks.
Yeah, because these open charms, they are mainly dominated by the light quark physics.
Yes. Yeah. So you're right. Open charm is like charm plus light quark, and it could be that it is the byproduct of the chiral phase transition, that some of the light degrees of freedom getting liberated, and because of
Also,
fine.
Okay, they're back.
Okay.
Yeah, they're
Where
back.
was I? Where was I when you people dropped? When the connection went off? Okay.
They are
Are
still
they-
muted. I think they'll
Yeah,
unmute.
sorry. So
The correct-
this is the correct slide. Yeah.
Okay, and I was answering your question, so I don't
Yeah,
know.
you are answering the question. Yeah.
But did you hear my answer
No,
or?
no, we got dropped out. Yeah.
Okay, yes, so you are right. Light quarks are affected by the chiral symmetry, and open charm hadrons have charm quarks and light quarks. And if light quarks are getting liberated, the deconfinement of charm quarks is a byproduct of that, right? But it still is deconfinement. And in the light sector, we cannot get this pressure because Boltzmann approximation doesn't work. But for the charm sector, we can actually see, we can actually get the contribution of these charm quarks to the total charm pressure, which is, I think, deconfinement. This is the order parameter for deconfinement. So, and the other thing which I was adding to this was like, one can also think about, trying to explain this PQC using the scaling arguments, and you can add, to the free energy, the energy-like directions to temperature plus the chemical potential of charm and do some calculation. I mean, I tried doing it, but till now, I don't think we can explain this PQC using the scaling arguments, like how it is related to the chiral symmetry. It's a bit difficult. And also another thing, I mean, if you solve for PQC, you would find it only the fact that alpha is negative for QCD plays an important role about how this PQC behaves. So that these are the only comments I have, and I think it is definitely.
You did not.
They're constantly actually trying. I just said that
You maybe minimize again.
I said I give uninterrupted. Do not touch the connection. Whatever is there, just give it uninterrupted. Today is holiday. It's does not happen like this. It's just a bad thing.
Should we just like postpone this talk because
But we have already started.
but like we can
Can wait.
Okay.
They are back.
They're back. Yeah.
Hello?
Hello.
Yeah, can you hear us?
Yes, we can hear you.
Sorry, we got again
Yeah.
disconnected.
Yeah.
Sorry, you were telling something and then we got disconnected. Please continue.
Yeah, I repeated the answer 2 times.
No, that's fine. I understood, but just my point is here that this is not a very good order parameter for deconfinement.
I think it is a good order parameter, and it's much better than the Polyakov loop.
No, I don't think
The parameters of dynamical quarks.
the good order parameter is the temperature dependence of the entropy density. That gives a very nice peak at TC, and that is the best order parameter that can tell you about deconfinement or these kind of systems.
I mean, order parameter not necessarily has to give you a peak. It can also be 0 in one phase and become non-zero.
The order parameter should capture the physics of deconfinement. That is captured by the entropy density, because when you have deconfinement, your entropy density increases rapidly. So that's how the temperature derivative shows a peak there, and that's how we know fundamental representation of quarks. We have a deconfinement and the chiral symmetry happening at the same. That's how we know. If of course the quarks were in adjoint representation, things were different. But I think that you should have calculated the entropy density and shown that if you want to really talk about deconfinement.
I would still say it is a good order parameter because it is increasing and it is also less noisy and it's directly tapping onto the charm quark pressure. It is in my opinion, it's a good order parameter, but we can discuss about this later, I think. Yeah. And the fact that this quasi-particle, it's a model, right? But you can question, I mean, what you're calculating could be total bullshit. Sorry.
Now, they probably already saw that near TC, the quark is not a very good quasi-particle. only becomes a good quasi particle a little bit ahead, like at 170, 180 MeV. So we cannot capture the physics near the.
No, I think in your paper you saw that around 175 MeV it starts dominantly contributing to the charm pressure, because ultimately from baryons and mesons the contribution will go down and the cross happens at 175. But that doesn't mean it's not a good quasi particle.
Not a
With
good quasi.
time the contribution is increasing, but I think at the only thing you saw at 175 was that 50% contribution comes from quarks and 50% comes from hadrons. Only after 175 quark becomes dominant.
I don't think it's a good idea. Continue. It is also it's also unfair on her. She is going to have to again give the same talk which she might not.
Not necessarily. She can start from here next time. Yeah. Like today our internet is like really.
You still have some 30 slides more, I guess. Yeah. So, yeah, maybe we can postpone this discussion towards the end of the talk and let Sipas continue with her rest of the slides.
Padmanabh.
Yeah.
So we are just discussing here, like Dhirajda has gone to like inquire with the computer team whether it is going to be unstable for the next like few hours. If that's the case, it like we'll be breaking out several times. So I don't know like whether we should be continuing like this or please.
I think we should continue because Sipas, she won't be able to like find another schedule easily. Since anyway she talked, we can just continue even if there is some slight break, I think.
Yeah, if it is like 20-30 minutes, then I think we can continue even if there are, assuming that there can be one or two breaks. I mean,
yeah, I think maybe we should just let her speak.
Yeah.
Unfortunately, with LAN, we never face this type of problem, but today there is some problem with the loops, etc. That what we said.
Yeah, maybe we can continue. So
Okay.
But I mean, so when you drop out, should I stop or should I keep talking?
You can just stop.
Yeah, better
But
stop.
I should know that you have dropped out.
Yeah, I will let you know.
Okay, great.
Yeah.
Okay, great.
Yeah. Chipas won't be able to see.
Yeah, sure.
Yeah, okay. So I am continuing and shoot your questions after the talk. Or I don't know, we can improvise. So it was a model, but we should be sure that it passes some validity tests. Okay, so these pressures, they took in, and we only went up to fourth order in calculating these susceptibilities, which means we still have another susceptibility left, which was not used in the construction. So one can write a constraint based on that, and this constraint means this quantity should be zero as long as they are quasi-particles with barrier.
Okay. I don't think so. I think it's a very bad idea to continue. But that's not the case. Like it's like most of the audience is here, right? It may not get solved. No, but like what we can do is in the evening, most of us will be in our homes. Someone can host the talk and they can record it on their device instead of it being recorded from here. It can be.
Is actually we record the talk. Okay, so you can actually try to. Can you hear me? Hello?
Yes, I can hear you. Yes.
Yeah, so media is also available. So even if they drop out, you can just continue. We will just record the talk and then share the rest of the talk with others so that they can listen to it. Okay.
Okay,
Yeah,
right.
Next time we are disconnected, please continue. Don't wait.
Yeah, so let me.
By the way, I'm not sure if you can record while they are disconnected, because I always get to hear recording stopped. So maybe someone else.
I will restart it. It means we can actually just restart the recording.
Can you record it on your device?
Yeah.
Okay.
Yeah. Yes.
Exactly. Yeah. So someone who's not in the media room should record it.
Yeah. I hope this works. Should I start recording?
Yes, please. Yes, please.
Okay. Oh, I cannot record because I am not the host. Can someone make me host?
No, I think whenever it is, whenever.
Yes.
Roji is a host, right?
No, Roji is not the host. I think media team is the host.
They can give.
I think it has been created by the media team, the link. It's one link. I think it has been created by the media team. And Gayatri or Shiva, they should be the ones who are the host. I think so. So unless we create a new Zoom link,
Make a co-host. Tell them to
Yeah, yeah, yeah.